So last Tuesday, we have solved the heat equations with boundary condition on the both end of the bar, such that the temperatures are 0. Okay, and and then at the end of the class, we talk about the situation that we assume different boundary condition that the two ends of the bar are insulated, so that there is no heat flow to both ends. Okay, and so at that situation, it affects the solution of our heat equation, especially that we have, I think, so the ODE okay. Okay. So we have the ODE. Okay. And in 12.6.4 with k equal to 0 or k equal to minus p squared, p greater than 0. Okay, such that okay, so with new boundary conditions, these two boundary conditions, then the ODE obtained from separating variables have non-trivial solutions. Okay, when k equals 0 or k is negative. Okay, and so that Okay, and such that so which are okay for k equal to 0, we have f0 x, which is equal to 1, and for k equal to minus p square. Oh, okay. By the way, I forgot when k is equal to, sorry, to minus m pi l square. Okay, and equal to 1, 2, 3, etc. Okay, and which are so when k equal to minus m pi, okay, then which are cosine m pi x of L, 1, 2, 3, etc. Okay, so these are new solutions. Okay, and so with lambda n defined to be c m pi divided by L for n from 0, 1, 2, etc. Now this case can be written as cosine 0 pi x L, right? So corresponding to n equal to 0. So now we can put together. Okay, so with this one, a non-trivial solution of the ODE. Okay, so the ODE governing G C square in 12.6.5. Okay, so it's Gn, which is an and e minus n square t for n equal to 0, 1, 2, etc. Okay, so now we multiply the corresponding solution of the two ODEs corresponding to the nth eigenvalues, lambda sub n. So this becomes 2an, and the cosine pi x divided by L e minus lambda n square t. Okay, so for all n to 0, 1, 2, etc. Okay, and x is in 0, L, and t greater than or equal to 0. Okay, and so a solution of okay, so the solution of the PDE in 12.6.1. So this is our heat equation. Okay. Together, will be U of xt, which is the summation from 0 to infinity, and the un xt. So that would be then general solution, I'm sorry, the E together with the boundary condition in 12.6.7. So the two boundary conditions here will be a superposition, right? And that it would be an cosine pi x divided by L exponential function with exponent minus lambda n squared t. Okay, so this is a general solution of PDE satisfying the two boundary conditions. Okay. All right. So now, and the coefficient S sub n can be determined by the initial condition. Okay, so by the initial condition, in 12.6.3, i.e. U x0 is equal to f of x, okay, for all x in 0 to L. Right. All right, so right. So now when we put the f of x becomes to be u x0, so that becomes to be summation n equals 0 to infinity n cosine pi x divided by L. Okay. And as you can see, which is the Fourier cosine series representation of f of x, okay, with a0, which is equal to 1 over L, 0 to L, f of x dx and an can be computed by this integral cosine m pi x divided by L and dx for n going to equal to 1. Okay, so that's we know what is that. Provided that f is continuous on 0 and L. Okay. So if f is continuous, then this representation is exact. Otherwise, this series sum is actually with a0, an computed this way is equal to the average of the left-hand limit and the right-hand limit of x at each point. Okay, so this is true when f is continuous at every point x in this finite interval. Any questions? All right. So if no question, then we will talk about a subject about steady two-dimensional heat problem. Okay. So this is about the Laplace equation. Okay. All right. So the heat equation. All right. With two spatial dimensions is the c square and the Laplacian operator u x y t. Okay, so which is equal to plus okay. All right. So so this is the heat equations with two spatial dimensions. Okay, so the temperature is a function of the two spatial variable x and y, and as well as the time t. Okay, all right. And in many situations, in steady state, that the temperature U will be time independent. Okay, in the situation, so that the two-dimensional heat equation becomes to Laplace equation. Okay, means that the gradient, the Laplacian of u, it's equal to 0. Okay, so this is called this equation. Okay, and for all x, y in a region, okay, which is the region. Okay, so and there are three ways to describe the boundary conditions on the boundary curve C of the region R. Okay. For example, if the region is a rectangle, right, in the plane, okay, then so this is the region, and the boundary, right, the boundary could be the four sides of this rectangular region. Okay, so this is the four sides of R. Okay, so for this example, and so there are three ways to describe boundary conditions. Okay, on the boundary curves. All right, and so we call first boundary value problem, BVP. Sometimes we call Differential problem. Okay. U is prescribed on C. Okay. Okay. So this is called the Dirichlet boundary condition. Okay. So we specify U, okay, the temperature itself on the boundary. Okay. So now this. Okay, so the equation together with such a maybe I think maybe I described. The Richlet boundary condition. Okay. U is prescript on C. Okay. So this is called the Richlet boundary condition. The second is called the Newman boundary condition, where the normal derivative, okay, so UN, which is defined to be, is prescript, okay, on C. Okay. So normal derivative, because we are talking about the derivative on 2 dimensions, so we must consider the so-called directional derivatives, okay, because that they are infinitely many directions, okay. Not like in 1 dimension, because in 1 dimension you have a positive direction, a negative direction, right? So basically there is only one direction, or you can say 2, right? One is x positive of x, the other is negative of x, okay. But in 2 dimension, in higher dimension, 2 dimension or 3 dimension, or in general n dimensional, then they are infinitely many directions, okay. So that we have to talk about the directional derivatives, and one of the important derivative is called the normal derivative. That means that the derivative we are considering derivative always perpendicular to the boundary. Okay, so for example, for the upper side, the direction the normal derivative would be the directional derivative, all right, in this direction, up direction. Okay. And for this left hand side here, the normal direction will be in to the waist, right, to the left. And here for the lower boundary, the normal direction will be down direction. Okay. And for here, for this part, the normal direction will be to the right. Okay. So that you have a different. So that this is called the normal derivative. Okay, so we just described the normal derivative on C. Okay, on C. So this is called the Newman boundary condition. This is the first one, second one, and third one. Third one is called the mixed boundary condition. Okay. So so U is prescribed okay on a part of the boundary C, and the normal derivative U sub n on the rest part of the boundary C. Okay. So for example, you may specify U on these 2 sides, and prescribe the normal derivative on the other 2 sides. So they are called mixed boundary conditions. Okay, so in general, there are three ways to describe the boundary conditions. Okay, and the Laplace equation together with the Dirichlet boundary condition will be called the Dirichlet boundary value problem. Okay, so that okay, so together with the Laplace equation in 6.9, right? We have, okay, so we have the Dirichlet boundary value problem. Okay, or just call it the Dirichlet problem. And similarly, together with the Laplace equation, we have Newman boundary value problem. Okay, so this is called boundary value problem. All right, and for the last one, together with 12.6.9, we have mixed boundary value problem. Okay. All right, so let's solve that. Now, so we now consider right the Dirichlet boundary value problem in a rectangle. Okay. So the situation is here. So there is a plate. Okay. So we have a plate here, and 0, x, and y. Okay. So here is A, this is B, and this point is AB. Okay. And along this side, okay, so A, y is 0 for all y in 0b. Okay, for this side, the temperature is 0, and U0y is also 0 for all y in 0b. So on this side, okay, and also x0 is 0 for all x in 0a. Okay, so on the bottom side, the temperature is also 0. But on the upper side, okay, the temperature will be f of x for x in 0 to a, and and of course, because of the two boundary conditions, they are all zeros. So we know f0 is equal to 0, and fa is also equal to 0. Okay. Right. So this is the restricted boundary value problem, because we prescribe the boundary values, okay, of U itself. Okay. So that this is clearly the Dirichlet boundary value problem, and we have the Dirichlet boundary conditions here. Okay. So any questions about? So we have a plate here. Okay. This is our region. This is our region. All right, and so step 1, separating variable. All right, so we let u of xy to be f of x and g of y. Okay. All right, so we know from physics that there must be one unique solution. Okay, so that because all the boundary, the temperature at at all the point of the at all point on the boundary are specified uniquely, right? So has been specified, and so the long run in the state states that the temperature at each point of this region will be determined uniquely, right? So sovereign variable give us this way to say that we let uxy is the product of two functions. One function is of x, the other function is of y. Okay. Okay, and now from the Laplace equation give us that we have this equation. So from this equation we have that f and d square f of x dx square is equal to 1 minus g of y, d square g of y, and dy square, and which we denote to be minus k, right? Okay. Okay, so now we have two ordinary differential equations. And okay. Now, for the and then we can see we have two boundary conditions for okay. So for x, okay, the boundary conditions, you see that so you know, because we have four boundary in this case, right? Now that 0 is equal to u 0y, right? And this is f of 0 and g of y. This is from the left side. How about the right side? A, y. Okay. And the lower side So we have okay, and the f of x is equal to u of x of b. So that is f of x and g of b. Okay, so we have that. And we are soliciting non-trivial solution. Okay, so in order to find non-trivial solutions, okay, so that g of y cannot be all 0, right? So that this implies that f0 is 0 and the fa is 0. Similarly, f of x cannot be all zeros, so g of 0 should be equal to 0. Okay, so from the first three boundary conditions, we get these three. Now, how about the fourth one? Well, this is the g of b, right? So that is f of x. So as we will see, that we will have about the g of b can be it's just a constant. So that means that f of x and the big F and the little f, they are proportional to each other. Okay? They are proportional to each other. So g of b can be arbitrary at this moment, right? Can be arbitrary at this moment. So now we have only, at this moment, we have only one homogeneous boundary condition here. Okay? Right? Okay? And so g of b can be determined, you can see, if we can determine f of x, because little f of x is given. But we can solve big F, right? From this second order ODE together with two boundary conditions here. Okay. Any questions? Okay. So now for k is equal to m pi divided by a square. Okay, so if k is this number, then we have non-trivial solution f of n equal to sine m pi x divided by a for n is 1, 2, 3, etc. Okay? Okay, so that for this ODE with these two boundary conditions, so I will see only, maybe I will say only for, okay. For other k, there is no non-trivial solutions. Okay, as we already have seen, we have already seen a lot. Okay, so we have the Fn here. Now, okay, with k equal to m pi a square, right? The OD right has a general solution. Okay, so this OD has a general solution. Gny to be an exponential m pi y a plus bn exponential minus m pi y a. Okay, for all n 1, 2, etc. Okay, so the second OD is there. Now, but with this boundary condition, but with G0 equal to 0, then we have that an plus bn equal to 0. Okay, so this implies that bn is equal to minus an, and then gn y becomes to be 2an and 2 em pi y divided by a minus a minus m pi y a. Okay, so we have this one. Because bn is minus an, and this number is the hyper sign, okay, hyperbolic sign. So this is a to an sine h of m pi y and a. Okay, for all n. Right, so we have a hyperbolic sign here. Okay, so the hyperbolic sign function is defined to be okay for all x in R. Okay, so this is the hyperbolic sign. I believe you have seen that before, right? Okay, so that we have a hyperbolic sign function here. All right, so now we define un xy to be their products. So fn x gny. Okay, so that would be, we will say an star, okay, sine m pi x a, and hyperbolic sign a. Okay, so this the sign function is from x, and this is f of x, okay, for all n from 1 to 3, etc. Okay, and then now Now, since the Laplace equation is homogeneous and linear, and the boundary conditions on the left, right button sides are homogeneous. Okay? Then if we take the series sum, okay? The series sum if it exists, right? If converges, okay? Satisfy the Laplace equation as well as, right, as well as the boundary conditions on the homogeneous boundary conditions, okay, on the three sides. Okay. Okay, so they satisfy 1, 2, 3. Right? Maybe I will say, so this is left side. This is right side. This is bottom side. And this is the top side. Okay. Okay, so let's take a short break of 5 minutes. 是那个财产，对，这个，然后这个是那个转移财产，也把它留下来好了。你需要这个吗？ OK。Okay. Okay. We have derived that this series sum satisfy our Laplace equation as well as the homogeneous boundary conditions on three sides. All right, and so the unique solution of the Dirichlet boundary value problem is to determine the coefficient n star. Okay, and this can be done by using the last boundary condition on the top side. Okay, on the top side. All right, so with the boundary condition on the top side, so we have f of x is equal to u of xb. Okay, so this would be summation from 1 to infinity and n star, and sine pi x a hyperbolic sine pi b a. Okay, so that this is equal to a n star sine h pi b divided by a of sine pi x and a. And it is clear that so which, right, which is the Fourier sine series representation of f of x. Okay, on 0 to a, 0 to a, and know that the f of x has 0 values at x equal to 0 and x equal to a. Okay, so that provided that f of x is continuous on 0a, right? And we should note that f of 0, f of a, okay, and this is true because of an x equals 0, so that this is exact. This representation is exact. So maybe I specify here. Since fa is equal to 0. Okay, so they are 0. So this, so for a sine series representation here, this one is exact. Okay. And we know that Bn is An star hyperbolic sine pi b divided by a, which is equal to this integral okay. So this is the Bn, right, in the Fourier sine series expansion. Okay, so this is Bn, and so from that, we know An star is equal to 2 divided by A and the hyperbolic sine pi b divided by A. Okay, and 0 to A, f of x sine pi x A and dx. All right, so finally, the unique solution of the Dirichlet boundary value problem is u of xy, which is equal to summation from 1 to infinity 2 divided by A hyperbolic sine of pi b divided by A. Okay, and 0 to A f of u sine pi u of A du, and sine pi x and A, and hyperbolic sine pi y divided by A. Okay, so this is the solution we have. Any questions? Okay, so we have solved such a problem. Okay. Okay, now we consider again the heat equation okay, but this time we are considering a very long bar. Okay. Okay, so we consider. Right. So in the previous section, we consider heat equation for a bar with finite length. Okay. Or we consider the Laplace equation on such a limited region. Okay. So, but now we consider the heat equation and now it's one dimensional, so that okay, we have only one spatial dimension x, but the bar is very long, so it's extended to the minus infinity and also to the positive infinity. Okay, and t is greater than u0. Okay, so we consider the heat equation. Okay, of the temperature U of xt of a bar which extends to infinity on both sides. Right, and also, and it's laterally insulated. And because the bar extends to infinity on both ends, so there is no boundary condition, right? So now, so we do not have any boundary conditions. Right, but only one initial condition. Okay, so U of x0 is equal to f of x for x in for all x in the real line. Okay, so this is our problem. Okay, and we call this is 12.7.1, and this initial condition is 12.7.2. Okay, so now to solve 12.71 and 12.7.2. We use again the method of separating variable again. All right, so we let U of xt to be f of x and g of t again. All right. So now this implies that we have f minus k, f equal to 0, and g prime minus k c square g equals to 0. Okay, so we will have two. So we will have two ODEs, right? One is second order, the other is first order, as before. Right? So we know that okay. Now for k is positive. Okay, a general solution okay of the first ODE in 723. Okay, is f of x equal to a of e p of x plus b e minus p of x. Okay. Right. So now we consider the first equation when k is positive. And so, so if A not equal to 0, if A not equal to 0, then the magnitude of f of x goes to infinity as x go to infinity, okay? So when x go to infinity, because p is positive, so this is go to infinity, okay? So when a not equal to 0, the magnitude goes to infinity, and which has no physical meaning. Yeah, because that we can't have such a solutions, okay? Because the temperature, the physical law for very long, for the temperature along such a long bar will be so the temperature cannot go to up to infinity, and so that this solution has no physical meaning. And similarly, if b not equal to 0, then the magnitude of f of x also goes to infinity as x goes to minus infinity. Okay, so when x goes to minus infinity, this part goes to infinity exponentially, which again, right? So which again has no physical meaning. Thus we have only trivial solution. F of x equal to 0. And then u of xt is 0. Okay? It's equal to 0. So in this case we have no non-trivial solution. Now for k equal to 0, okay, and we find general solutions of the two ODEs. Okay, so we solve when k equals 0, so we find that f of x is ax plus b, and g of t is c. Okay. Now, if a not equal to 0, so if a not equal to 0, then the magnitude of f of x goes to infinity as s goes to minus plus infinity. Okay. Again, which has no physical meaning. All right, so a must be 0. Okay, and u of x t 0. So here we put 0 here because this corresponding to k equal to 0. So this is b and c. All right, so which is a constant function. Okay, so it's a constant solution, of the heat equation. Okay, of the equation here. Now the last case for k is negative. Now the two ODEs become f double prime plus p square f equal to 0 for x in R, and g prime plus c square p square g equal to 0 for t greater than equal to 0. So the two ODE becomes there, and their general solution. So we can find their general solutions. All right, f of x p, right? So p is parameter. A1 equal to A1p cosine p of px plus b1p, and the sine px and for this first order ODEs, the GTP is equal to CP and E minus C square P square T. Okay, and where A1P, B1P, and CP are arbitrary. And dependent only on the parameter p greater than 0. Okay. Any questions? Yes, please. Oh, okay. Because they are general solutions, and so to determine a unique solution, you may need to specify either boundary conditions or initial conditions. But when you specify boundary condition or initial conditions, to determine the coefficients there, it will in general depends on the p here. Okay, it will depend on p here. So that we just give the explicit dependency of these coefficients, okay, on the parameter p. It's kind of we are foreseeing that to determine the coefficients, because you are given a boundary condition. The boundary conditions are given, for example, some specific value, right? For example, 0, 0, or 0, 1, etc. for the boundary conditions. And you will see that when you determine the coefficient from the boundary conditions, that will depends on the parameter p. If you have the experience, because we have solved a lot of this kind of ODE in several places, so that it will depend on the parameters. Okay. Other questions? So in summary, all right, we form the solution AP cosine px plus bp sine px together and exponential minus c square p square t and x in R. Okay. Because we multiply the f and the g together. Okay. Oh. Yeah. And you can see AP is just the product of A1P and the CP, right? And the BP is the product of B1P and the CP. Okay, so they can merge together. Okay, so this one is a solution of the heat equation. In 12.7.1, and call the eigen function of 12.7.1 corresponding to the eigenvalue lambda of P, which is defined to be Cp for all P greater than equal to 0. So if P equal to 0, we know for P equal to 0, this is 0, okay? And this is 1, okay? And this is 1. So this come to a constant, right? We can do a constant only. Okay. So this is corresponding to the constant solution. Where is constant solution? Oh, here. So that we have the constant solution here. Okay. Okay, so we merge together. So now we have eigenvalue, right, which is continuous. Okay, so which is continuous. Okay. So any p, right, greater than or equal to 0, for any p greater than or equal to 0, this is a solution of the equation here. Okay, p can be any non-negative number, any non-negative number. Okay, so that's a lot. They are different from the previous section, right? The p will be discrete value, right? P are discrete values. So, but here we have continuous eigenvalue lambda here. Okay, but we have initial condition, right? So that this equation is very hard, right, to satisfy the boundary condition, except that f of x are spatial type. Okay, because that the u of x 0 p, we know that when t is 0, so this is the AP and the cosine p of x, px plus bp sine px. Right? So that this is the solution if and only if this is equal to f of x. Okay? F of x. Okay. F of x for so that is very special, right? Very special case. So now, how do we find a solution? Okay. Now again, the Higgs equation is linear. Okay. So and also homogeneous. Now, since the Higgs equation is homogeneous and linear, okay, any superposition of eigenfunctions of the Higgs equation okay, is also a solution okay, of the Higgs equation. All right. Now, but since the spectrum okay is continuous, any superposition of the eigenfunctions will be represented by an integral. Okay, so now we see the integral. So u of xt equal to from 0 to infinity u of xt with parameter p and dp. Okay. So which shows that the contribution from each eigenfunction is differential. Okay, because we have uncountable many eigenfunctions. Okay, and so that we will have AP cosine px plus BP sine px e minus c square p square t and dp. Okay, so this one, and so this is our candidate, right? Our candidate, and but we have to show that this integral. So we have to show that we will show so this integral we say 12.7.4 is indeed a solution, okay, of the heat equation. In 12.7.1. Provided that AP, BP, and P square AP and P square BP are absolutely integrable over this interval. Okay. So if AP, BP, so they are a function of P, and P squared times AP, P squared times BP are absolutely integrable over this semi-infinite interval. Okay. So if this is the case, then so that this integral is a solution. And we can use, so we now use theorem 11.7.b in chapter 11, which is a theorem about differentiation under the integral sign. To show which is justified, whose usage so we will use theorem which is justified in the lecture notes, supplemental lecture notes. Okay, so please read the lecture notes, okay? Because I will not describe the detail, but I have justified that why theorem 11.7.b can be used. Okay, so that means that we can do so the differentiation and the integration can be exchanged, the order. Okay. All right. So please see the justification. Okay. All right, and so now the derivative, okay, with respect to t. Yeah. So that it would be so this is equal to AP cosine px plus BP sine px e minus square p square t and dp. Okay. Now we can exchange the order of integration. So the partial derivative is respect to t, but this part is independent of t, right? So we have AP cosine px plus BP sine px. But the derivative we have would be minus c square p square and e minus c square p square t dp. Okay? Okay, so this is, so now we can have minus c square, and we have p square ap cosine px bp sine px exponential minus c square p square t dp. Now, and the second partial derivative of u with respect to x. So okay, so now okay, so now because it's with respect to x, so you will work on this sum here. Okay, so we have px p here. Okay. And so this is equal to minus p square AP cosine px plus BP sine px minus dp. Okay, so when you compare them together, so you will see that it's equal to c square okay. Right. All right. So that so we have the required equation here. So you can see that this integral, right? This is superposition of eigen functions. It's a solution of the heat equation. Okay. And that AP, BP, and because that if AP is absolute integrable, BP is absolute integrable, then this integral exists. Okay, because this part, this exponential function has value upper bounded by 1, right? And the cosine sine function has magnitude upper bounded by 1. So that if you take the absolute value, you will see that AP and BP, when AP, BP are absolutely integrable, then this integral exists. And similarly, this integral and this integral exists if p square AP are absolutely integrable, p square BP are absolutely integrable. Okay, so this condition, the absolute integrability guarantee that this integral exists, and all the partial derivatives are also exist, so that and they satisfy the heat equation. Okay, so that is the basic things we have checked. All right, and with that, we can see that. So now we now are able to determine AP and BP by the initial condition. As follows: the f of x is equal to u of x0, okay? And as you can see from here, when t is equal to 0, this is 1. So that we have AP cosine px plus BP sine px and dp, okay, for all x in R. And when you see this one, you recall the material we learned in chapter 11, which is just the Fourier integral representation of x, and is valid with its value with AP. So AP can be computed with 1 over pi of this integral. And BP is 1 over pi minus infinity to infinity f of u sine pu and du for all p. Okay, right? And this representation is guaranteed, right? If by our Fourier integral theorem, right? So if f is continuous and absolutely integrable over R and has the right hand derivative and the left hand right at every point in R, right, by the Fourier integral theorem. I.e. Theorem 11.7.1. All right. So this is immediately the application of our Fourier integral representation theorem here. Okay. Okay. So I stop here.